All right, so let's go ahead and get started with lesson 5.1 and 5.2. So here we're going to use trig substitution to write an algebraic expression as a trig function of theta, and using this restriction here from theta is between 0 and pi over 2. Now this is important when we are working in calculus. So we're going to use this trig substitution to help us simplify integrals and derivatives and things like that in the future. And so right now you might think, well, why would I want to do this? But it's because the applications of it for the future are going to be great. So we want to be able to make sure that we can do it. So once we hit those calculus topics, we know how to manipulate and work with those calculus topics. All right, so it gives us our trig expression here. And then we are also given what we are going to do our substitution with. So we're going to take this expression here, this 9x squared plus 4, square root of that whole thing. We're going to substitute in 3x as 2 tangent of theta. This problem gives you that information, but when you get to calculus, one of the things that you're going to need to do is you're going to need to figure out what should you substitute and why for each of the problems that you're working with. Okay, and that's going to come with knowing and understanding all the trig identities really well and knowing how you can manipulate those trig identities so that you can get something that you can work with for whatever that problem is asking you to do. So here we're just going to take what was given to us. So we're going to say, okay, well, this then is going to be equal to, I'm going to do the square root of, and I'm just going to rewrite this one step. You don't actually have to do this every time, but I'm going to rewrite that so we can directly see our substitution. And so now we can see exactly where we're going to substitute in that 3x. So we have this 3x right here, and we're going to plug that in for this 3x inside there. So continuing on, we have that this then is going to be equal to the square root, and I'm going to put in the quantity of 2 tangent theta squared plus 4. So now I'm going to start to simplify this. So, all right, simplifying. Square root of, now I have 4 tangent squared of theta plus 4. And just a quick note on the side, whenever we have like tangent squared of theta, we know that that's tangent of theta times tangent of theta. So that's equal to tangent squared of theta. It's also equal to tangent of theta quantity squared. Okay? And now we always write it on like I have on the first line, but this is how you input in your calculator. Because we can't put the square in the middle. But when you write it, we write it this way. So this is what we write on paper. And then that's what we'll input into the calculator. So just know the connections between those two different notations and know when and how to use both of them so that you can use them properly in each of the cases. All right, so continuing on with our simplifying, we're going to factor out the 4, so square root 4 times tangent squared of theta plus 1. Now I'm going to use my identity. So an identity that I know that 1 cos tangent squared of theta is equal to secant squared of theta. So I can substitute that tangent squared plus 1 with my identity. So now I have the square root of 4 secant squared of theta. The reason why that's helpful is because now I have 2 perfect squares, and it's a product of 2 perfect squares. So I can take the square root of each of the pieces of the product. So I get 2 secant theta, but I do need to remember to put absolute value around those. Because whenever I put absolute value around those, or whenever I take the square root of something, my square root is positive, so I need to guarantee that that's positive. Okay? So I put absolute value around them, but then the last thing I want to do is I want to evaluate that absolute value, make sure that I need it. So I'm going to ask myself this question: is the absolute value necessary? And the way I figure out if that absolute value is necessary, I'm going to check the restriction on theta. So we go back up to our restriction right here. So we have 0 to pi over 2. So I think about that on the unit circle. 0 to pi over 2, that's going to be quadrant 1. So in quadrant 1, is the secant always positive? Is it always negative? Or could it be sometimes positive, sometimes negative? The answer to that question tells you whether or not you need the absolute value. So because that is always positive, I don't actually need the absolute value. So I'm going to take the absolute value away and just write it as 2 secant theta. Because I always want to write it in the simplest way as possible. So if I don't need the absolute value, I don't want to have it there. Okay? All right. If theta were between, let's say, between pi over 2 and pi, then we know that secant in quadrant 2 is negative. So we would need to keep the absolute value in there. Okay? But whenever we don't need it, we don't want to put it. All right, so moving on to number 2. This problem here is a verify problem. And this verify is really the same as me saying, okay, let's just prove this. So it's the same as saying prove. So we're going to do this problem just like we do all of our other proofs. Okay? I'm going to choose to work on the left. You could choose to work on whatever side you want, but I'm going to choose to work on the left. And what I'm seeing is the left-hand side is 1 term right now. The right-hand side is 2 terms. So I have that plus sign if I were to distribute that secant squared in there. Okay. So I'm going to figure out how do I make the one side equal the other. And I'm going to break up the left side into more terms and keep the right side kind of how it is. All right. So working on the left here. I also see that I have this secant squared here on the right. And so I'm going to take this secant to the 4th, and I'm going to start with that. I'm going to turn that into a secant squared times a secant squared. So that I have the secant squared piece that I want. So let me go ahead and start by breaking that piece up. So I'm going to say that this is going to be secant squared of x times secant squared of x. And then I still have my tangent squared of x equals. Okay, so now I have this secant squared of x, which is what I want. So that matches this piece right here. Okay? And so I need to turn the rest of this secant squared, tangent squared, into that part right there. You kind of follow the colors along, kind of guide you into where you're going. So I can see everything that's in the blue on the right-hand side is tangents. But on the left-hand side, I have a secant squared comes with tangent squared. Oh, but I have an identity, right? I have an identity that changes secant squared into something with tangents. So my identity that I'm going to be using here, I know that 1 plus tangent squared of x is equal to secant squared of x. So that means that secant squared of x is, I don't know why are we writing that? Is 1 plus tangent squared of x. I don't know, I guess I just wanted my secant squared on the left-hand side. Okay. So I'm going to go ahead and I'm going to substitute that. So I have my secant squared of x still. So my first secant squared of x. I'm going to substitute now the second piece of it into 1 plus tangent squared. All right. And so now I have 1 plus tangent squared of x, or put that into a parenthesis. And then that's multiplied by a tangent squared of x still. I guess I'm in moment parenthesis. My equal sign is getting out of whack. All right. And now I can see all I need to do is just distribute that tangent squared and then rearrange my terms. So I'm just going to go ahead and distribute the tangent squared and then I'll rearrange on the next step just to keep it consistent. So then I have a tangent squared of x, and then I have a tangent to the 4th of x. And then I'm just going to switch around my terms. So I have tangent squared of x plus tangent to the 4th of x, that quantity, times secant squared of x. Don't forget to write the right-hand side again, so you have that for your final indicator. And we did it. Yay! Great, so problem number 3 is a little bit different, but it's still a verify, so we're still trying to prove this. But we are going to do it a little bit differently because we have an inverse in here. So we know that an inverse represents an angle, right? So this inverse sine of x represents some angle. And then I'm taking the cosine of that angle. So I don't have a way to find out what that angle is, but I can draw a triangle in a diagram to manipulate my way through this problem. So we're going to do it in a similar way. We're going to be doing the left column, the right column, but we have to add one more step here. We need to define something to use in this problem. I'm going to define on the right so that I can keep my proof on the left-hand side. All right, so on the right-hand side, I'm going to say, well, let's define this angle the inverse sine is equal to. So I'm going to say, let's let theta equal inverse sine of x. So if I let theta equal inverse sine of x, then my problem just becomes, on the left, the cosine of theta. And I want to prove that that's equal to the square root of 1 minus x squared. Okay? So if theta is equal to inverse sine of x, then I know that the sine of x is equal, the sine of theta here is equal to x. And I can draw a diagram to represent that. So I'm going to draw myself a triangle and put my theta in here. Sine of theta is x. So this is like x over 1, right? X over 1. So opposite is x. Hypotenuse is 1. And now I can find my making side. So you don't have to set the word for this. A squared plus x squared equals 1/3. You can if you want to. So I get a squared equal 1 minus x squared, and a is equals this divided by minus x squared. So that's this missing side here. 1 was squared plus x way. Well, now I just find the cosine of that. So using this diagram, a problem says cosine. So cosine, we know, is going to be the adjacent over the hypotenuse. So in our problem, cosine of theta is the square root of 1 minus x squared over the hypotenuse. Or convert the square root of 1 minus x. So we did it. So we just have this little added piece here where we have to define the variable so that we can then continue on with our problem. So here we have another verify problem. And it's not that it's really that hard, but the thing I want to call your attention to is the fact that we got this absolute value on the right-hand side. So we have more square roots, so we have to think about our absolute values again. And with that absolute value on the right-hand side, one thing that you don't want to do is you don't want to just say, oh, okay, I see absolute value there. And then you manipulate this. You get down to 1 minus cosine theta over sine theta. And what you don't want to do is you don't want to say, oh, let me look at the right-hand side. Where am I trying to go? Those are my eyeballs. Oh, I see I have absolute value of the denominator. Oh, let's just throw absolute value in there. Oh, I did it. That's fine, but you want to make sure you know why you have to have the absolute value. You don't want to just simplify and get to a point and say, oh, I'm going to throw it in. Maybe you'll get full credit, but you're not going to understand fully what you're doing. Also, I like to ask these kinds of questions, right? So maybe I won't ask you to prove this. Maybe I'll give you the proof, all completed. And my question to you will be this. Why did you put absolute value here? Explain it in a sentence. Okay. And that's what you're going to have to do. You're going to have to explain that. So you don't want to just look at the right side and say, oh, I see absolute value, let's put absolute value. You want to make sure that you know why. So if and when, however, when you ask that question, you can answer that question. Okay, so let's work through this and let's figure out why that absolute value is there after we simplify and get down to everything that we have. Okay, cool. So just starting by simplifying, I say in my denominator I have sine theta. Let's first work on that denominator. Works out nice because my current denominator is 1 plus cosine of theta. And with that current denominator of 1 plus cosine of theta, all I need to do here is multiply by the conjugate of 1 plus cosine. So I'm going to multiply the full thing by 1 minus cosine theta. 1 minus cosine theta. Right? Like, because it's around there, so I'm making it very clear. Square root is at 1 minus cosine theta over 1 minus cosine theta. It's still 1, so it's fine to multiply by that. And now when I simplify in my denominator, I'm going to get 1 minus cosine squared. My numerator, it's 1 minus cosine times 1 minus cosine, so it's 1 minus cosine quantity squared over 1 minus cosine squared. They sound very similar, but they're very different. 1 minus cosine quantity squared versus 1 minus cosine squared. So now I'm going to use my identity, right? My identity that I can use here is I can say that sine squared theta plus cosine squared theta equals 1. So 1 minus cosine squared theta is equal to sine squared theta. So that's what I'm going to use there. And resubstitute 1 minus cosine squared as sine squared. Not 1 minus cosine quantity squared, but my denominator is now sine squared. Perfect. Well, now I have a numerator that's a perfect square and a denominator that's a perfect square. So I can do happy cancel. Happy cancel. The square root cancel this square and that square. When I do square root, I must put my absolute value. So now I have the absolute value of 1 minus cosine theta in my numerator over the absolute value of sine theta in my denominator. So this is where you want to ask yourself, why do I have absolute value in the denominator still in what I'm actually carrying through, but it disappeared from the numerator? And this is where you don't want to just go, oh, just take it out of the numerator, leave it at the denominator, and just move on. You want to make sure that you understand why. So you want to be able to answer this question. Why keep the absolute value in the denominator, but not the numerator? All right, so thinking about those restrictions on cosines and sine, right? So denominator sine by cells can be negative or positive, swing negative more at once to different day. So we need the absolute value. But yeah, that 1 minus, so if I do 1 minus cosine, 1 minus negative 1, so we need positive number. 1 minus positive 1 here is also going to give me a positive number. 1 minus anything in between negative 1 and positive 1 is also a positive number. So I don't move it. All right, so I just end up with 1 minus cosine theta over the absolute value of sine. And that is exactly what I liked it. And I not only got it right, but I also can explain why the absolute value is only where it is. So do make sure that you have this step in here, this is key. Okay, so you copy absolute value on both, and then you simplify it to where you only need any. And you not only kind of use the right-hand side to help guide you there, but you also have a reason to explain why that happened. What we're going to do in this one is we're going to use our graph and calculator. So we'll use the graph ability to put the left side as one equation and the right side as another equation. And then we're going to see where those two equations can set. So what you're going to write down are the cadence. This isn't really important. This is a work that isn't info on graph and calculator columns. You're going to put, let's let y1 equal, tell me what you're going to plug into y1. So y1 is tan to update us. And then you're going to let y2 equal the right-hand side with this square root of secant square of theta minus 1. You don't want to use identity and manipulate that at all, because that's the whole point of what we're doing here. So you want to type it in exactly how it is. However, you don't have a secant button that calculated, unless you have a CI Aspire. And so what you're going to need to do then is you're going to need to change that secant squared into 1 over cosine squared. And I'm going to write it as 1 over cosine theta quantity squared. Remember at the beginning I said that's how you have to type it into calculator, because you can't insert the square in between the cosine and the theta with the s. So 1 minus cosine x quantity square is how you type it into theta. So we type those in as our y1 and our y2. And then what we're going to do is we're going to find the intersection points. And I'm putting points because it could be more than one. It could be a region. In this case, it is going to end up being a region. And there's going to be an input. So they gave us that our window you want to look in is from 0 to 2 pi inclusive on both of those. So let's go ahead before we even graph it. Let's try to set our window range. So on your window, your x's, we want to go from 0. So x min is 0. X max
we're going up to 2 pi. If you want to go a little further than that so you can see the actual endpoint, you can do that.
And then you might want to change your x scale. So the x scale is what your calculator shows the tick marks for. Okay, so x scale, I usually start with pi over 2. And then I see what my graph looks like. And if I need to figure out other tick marks, I'll be changing to pi over 4 or pi over 6 of wherever I think the boundaries are going to be for the problem. Then your y doesn't really matter so much. So you can just do your y min as -10 and your y max at +10 if you'd like. I think that we're ready to graph. Now my recommendation is to graph them one by one. And so when you're plugging these into your calculator shows a highlighted equal sign. So like right here, this equal sign will have a box that's like black, gray, I guess. And that means that that's going to be turned on and it will graph that. If you arrow over to the equal sign and plus insert, it will take away that gray box and it's not going to graph that equation. So I would graph y1, then I would turn it off, and then I would go back and I would graph y2 by itself, see what they look like by themselves, and then graph them together. If you have a color calculator, easier to see than if you have just a like the grays and the other colors out for. So gray and gray and it. Calculator is harder to see without graphing them separately. Okay, so go ahead and graph those on your calculator. Get that information plugged in, and I'm gonna go ahead and get that ready on Desmos. Okay, so here we are on our graphing calculator, and you can see I have no graphs turned on right now, and I'm gonna turn on the graphs one by one so we can see what they look like. And I did make my my x-axis go a little bit past 0 and a little bit past 2 pi so you guys can see the endpoints on here. So if I turn on tangent, we should already know what tangent looks like, but there's what we see for tangent. That looks like our tangent graph. That's perfect. So that's in red. I'm going to turn off tangent, and then I'm going to turn on secant squared minus 1, square root of secant squared minus 1. And that's what that looks like. Oh, interesting. Okay, so I've seen both of them independently. I can see that those negative regions of tangent don't exist on this secant squared, square root of secant squared minus 1 graph. So let me go ahead and turn tangent back on. Oh, when I turn tangent back on, I can see that overlap. I don't know if you guys can see the color differentiation on my screen here, but you should kind of be able to see that this blue that's right over here is a little bit different than this blue that's there. This blue is kind of darker because that's the overlap part of the blue. And so we have these intervals that are regional. So we're going to start from 0, and all of this part here is then going to be overlap. So that's going to be included. So I'm just going to type the solution here on this third line of my Desmos. So I want to think about the endpoints as well. So when I start at 0, does 0, oops, wrong keyboard. If I start at 0, I'm going to go from 0, it looks like, to pi over 2. So 0 to pi over 2. I need to think about, do I need brackets or parentheses though? So if I think about the left-hand side, is that 0 here? Is the 0 included or is it not included? So we want to include that point at 0. So I'm going to put a bracket on the left-hand side there. So bracket, nope, wrong bracket, bracket. Now the right-hand side. Do I have a bracket or do I have a parenthesis on the right-hand side? Well, that right-hand side is pi over 2. Well, there's not a point there, so that's going to be a parenthesis because that's an asymptote. So parenthesis there. Then union. And I look at for where do I pick up next? So where do I pick up? What do you guys think? Where do you pick up next? William?
Pi.
Perfect. And then where do we end?
3 pi over 2.
All right. And do we include pi? Is pi a bracket or a parenthesis? Sophia?
Bracket.
Cool. And then 3 pi over 2?
Parenthesis.
Good. All right. So we have a bracket here. Where's my bracket? Bracket. And that's at pi, comma, 3 pi over 2. Parenthesis. Yeah, I got an extra. That's not what I want to do. Parenthesis here. There we go. And then at the very end, I look at the very end point. So I can see that I do meet at 2 pi. And so I want to think about, do I include that 2 pi or do I not include that 2 pi? And for that, I want to go back to the restriction that was given in the problem. and I look at the restriction in the problem. Because they do meet at 2 pi, if the restriction includes 2 pi, I want to include it. If it doesn't include 2 pi, I don't want to include it. So my restriction in the problem that was given was inclusive of 2 pi, so I do want to include it. So union, and then I just have a squiggly bracket, and then just put 2 pi. And then I close my squiggly bracket. And there's my answer for the solution to that equation using my graphing calculator.